The location of electrons in an atom can be described in a couple of different ways. Individually, we can identify any single electron within an atom's complement using quantum numbers, which uses an addressing system that consists of 4 values. Collectively, we can identify the arrangement of all of the electrons that an atom has using orbital diagrams and electron configurations. This lesson will focus on these. Electrons fill in around the nucleus, occupying the orbitals and sublevels in order of increasing energy. This is referred to as the Aufbau Principle. Aufbau is German for filling up. Lower energy level orbitals and sublevels should be filled in before starting a higher energy sublevel. Remember when we looked at the Bohr model of the atom, we saw that the principal or main energy levels, the rings, became closer and closer the further we moved away from the nucleus. At the same time, each of these main levels, the further we get from the nucleus, is going to have more and more subdivisions or sublevels. And so the problem that we run into is that eventually these sublevels are going to overlap one another. Some of the higher sublevels, the D's and the F's, are going to have energies that are more analogous to main energy levels or principal energy levels that are further away from the nucleus. In the first place we see this overlap is between the third and the fourth main energy levels. If we consider the third principal energy level, we have the 3s, the 3p, and the first instance of a d sublevel, the 3d. When we consider, however, the fourth main energy level, the 4s sublevel is actually lower in energy than the 3d level is. And so consequently, according to the Aufbau principle, after 3p is filled, the 4s would be the next orbital that would be filled in, followed then by the 3d. And so we get this overlapping that occurs. And the further out we move from the nucleus, the more often this overlap is going to occur. The diagonal rule is one tool that can be used to help determine the proper order of sublevel filling. The construction of the diagonal rule is pretty straightforward. Each row would be a different principal energy level or main level, and then each column are the different sublevels, S, P, D, and F. And so what you would do to finish the construction of this is to draw parallel arrows going diagonally through these sublevels, and then what you would do to write the configuration is start at the very top with the first arrow and follow each arrow from tail to head. And as you pass or encounter a sublevel, you fill that sublevel into its maximum capacity. When you reach the head end of an arrow, you simply circle back to the next arrow, the tail end of it, and you continue serpentining your way down through the diagonal rule until you have distributed all the electrons. Another tool that can be used is an orbital diagram in which each of the sublevels and their corresponding orbitals are represented either by boxes or even circles, sometimes even just an underlined section representing a given orbital. And these are usually set up such that the sublevels and their varying energies are depicted by being at different elevations as you move up the diagram. And so as you would fill in the electrons according to the Aufbau principle, you would start at the bottom, fill in each orbital to its capacity following the rules of Aufbau, Pauli exclusion principle, Hund's rule, and continue your way up the diagram until a point in which you have distributed all of the electrons for that given atom. We document the distribution of electrons in a configuration using orbital notations. Orbital notation consists of 3 characters: a coefficient, which represents the principal or main energy level the electron is in, and can also help us determine which row of the periodic table to find an element; the letter, which represents the sublevel the electron is in and tells us which general block of the periodic table an element is in; and an exponent, which communicates how many electrons are in the sublevel and indicates the column within a given sublevel block that we can find the element. In 1925, Friedrich Hund showed that when filling in a sublevel that has multiple orbitals of equivalent energy, these are known as degenerate orbitals, The electrons will fill in one to an orbital before pairing up. This is known as Hund's rule. Hund's rule also states that the spin of these initial electrons should all be parallel. This mainly applies for drawing orbital diagrams. Also in 1925, Wolfgang Pauli showed that no two electrons' quantum number sets, used for identifying individual electrons, can be exactly identical. Essentially, this means that when two electrons need to occupy the same orbital in the same sublevel, they must have opposite spins. This is referred to as the Pauli exclusion principle. When electrons are distributed in accordance with these three guidelines, we have what is referred to as the ground state electron configuration.